Hello and welcome all of you. Welcome to Electromagnetics for GATE, Electronics and Electrical. Electrical students, your syllabus may be less, but there is good weightage in GATE. Electronic students, your syllabus is very vast and also there is equally good weightage. The subject starts from as basics as charge, static electric fields, 12th class syllabus, and goes to as advanced as antennas, Maxwell's equations, electromagnetic waves. So EC students, you have a vast syllabus. Electrical students, you have a short syllabus. Whatever it is, the syllabus spans completely from basics, from charge, voltage, network theory, KCL, KVL to antennas. Also, the subject is not a single semester subject in your BTech. It comes into wide different times, maybe in second year, maybe in third year, at different times it comes. Whatever it is, electromagnetics is a very vital subject. You have 8 to 9 marks in GATE. Typically, let's say 9 marks out of the 100 marks. Electrical students, approximately 5 marks, 3 questions or 2 questions, approximately 5 marks. So typically students, I can tell you that EMFT is one of the toughest, one of the interesting subjects and also one of the scoring subjects. The good news about GATE exams last 3-4 years is they are not touching the tough topics like antennas. Reasonably, GATE has become quite simple for EC students and electrical students because they are not touching the most critical areas. So EMFT or EMT, sometimes called as EMTL, is a very interesting subject. Look at the modules that you have to learn here. What are the modules I'm going to handle? The first module is all about static, electric and static magnetic fields. So on the whole, I call it as static fields. It handles electric and magnetic. Both will handle both of them simultaneously. Then comes the second topic, the easiest, electromagnetic waves via Maxwell's equations. Through Maxwell's equations, we'll be learning electromagnetic waves. The third chapter is equally simple. It's about voltage and current waves extending to electromagnetic waves. It is called as transmission lines. Actually, nobody uses the heading VI waves. They call it as transmission lines. I called it as VI waves. The fourth chapter is also about electromagnetic waves, but it's about guiding of electromagnetic waves. It's called as waveguides. How we guide electromagnetic waves, confining them, how an optical fiber is designed, and those basics. The last chapter is antennas, considered to be equally tough, just like the first chapter, because the first chapter is actually supposed to be the toughest chapter. The first chapter is actually supposed to be tough. Equally, antennas is also supposed to be tough. Electromagnetic waves, Maxwell's equations is quite easy. Transmission lines is also easy, whereas waveguides is not that easy, so I'll call it as moderate. On the whole, 8 to 9 marks out of 100 marks in GATE. So interestingly, good weightage, interestingly good coverage. We'll start the subject. We'll understand how to handle the subject. We'll look at what are the basics in the subject. Let's look at the syllabus in the subject once. That is, when it starts with static fields, you cannot directly start static fields. We cannot directly learn electromagnetic fields until unless you have a good idea of mathematics, unless you have an idea of 3D space, 3D geometries, integrations, differentiations, vector calculus. So we actually need coordinate systems. Generally, you cannot expect questions from coordinate systems, but in GATE 2024, there was a question from coordinate systems. There was a question directly from coordinate systems, so you have to learn it. Then comes vector calculus. These are the two prerequisites, and you can expect exam questions also. There are quite a few exam questions even from this area. So, coordinate systems and vector calculus. After that starts understanding of Gauss law. And when you are learning Gauss law, remember that you should learn Ampere's law parallel to this. And do the theory for various geometries. Apply these two laws for various charge or current shapes. So if you are confident with coordinate systems, if you are good at basics, you can move on easily to Gauss law and Ampere's law and do the problems or handle the charge geometries. Handling a point charge, line charge, sheet charge, volume charge, cylinders of charge, infinite line, finite line, lot of geometries will be there. In fact, every geometry you have to handle, every current shape you have to handle. So that being the basic area, then starts simpler topics like potential calculations. In electric field, you call it as EMF. In magnetic field, we call it as A bar, vector potential A bar. Similarly, we talk about forces, Coulomb's law. We talk about Lorentz law. We talk about electric and magnetic force acting. They're all relatively simple topics. Then comes boundary conditions. Handling boundary conditions in electric fields, handling boundary conditions in magnetic fields. Then comes the understanding of capacitors and inductors. You learn capacitors, you have to learn inductors. Then comes the concept of induction in static fields. Then comes the concept of Faraday's law. So on you have to handle multiple things like this. And I'm almost summarizing the subject actually. I'm maximum trying to tell you what are the contents in the subject, and that too in only first chapter still see. Now if I go to second chapter and all, still you have lesser topics. But see in first chapter how many topics you have got, see. See how many topics you have to handle. Starting from coordinate systems, vector calculus to Gauss law, Ampere's law. From there moving on to potential, EMF, force, boundary conditions, capacitors, Faraday's laws. Lot of topics, students, lot of topics, and every topic has got equal weightage. If you finish off all these things, then ends actually. In fact, the subject starts, but first chapter ends. That is Maxwell's equations. Actually, the entire first chapter is about Maxwell's equations only. This is the heart of the subject. You have to fall in love with Maxwell's equations. Then is when the subject is interesting. So no doubt you may learn boundary conditions, you may learn potential, you may learn EMF, you may learn that, you may learn this. But the love is Maxwell's equations. That is the center of the subject. So if you finish off Maxwell's equations, using Maxwell's equations, we will actually move on to understanding of electromagnetic waves. So that we understand electromagnetic waves and their propagation in various materials, lossless, lossy, dielectrics, conductors. So we try to handle electromagnetic waves and their propagation in lossless, lossy, dielectrics, conductors. We try to understand electromagnetic waves through all these materials. Then we move on to understanding of what is polarization. Actually supposed to be easiest topic. Then comes power calculations. Then comes reflections under normal incidence and reflections under inclined incidence. This is the entire second chapter. So watch that second chapter could almost be filled up in one page actually. Whereas first chapter I could not fill it up actually, see. I think I needed almost 2 pages. Though I could have filled up these places. Typically if you look at second chapter, I could almost finish off in 1 page and leave some spaces here and there. But whereas first chapter if you watch carefully, I am not left with any place after writing so many things. So I hope you are getting the depth of the first chapter. In fact, remember that I have condensed first chapter as static and electric both. Electric and magnetic both. Static, electric and magnetic both. Otherwise in some teachers they say electric field is different, magnetic field is different. That is chapter 1, this is chapter 2. Even in BTech syllabus also, you learn electric fields, you learn magnetic fields. I mean you learn separately, electric fields, Gauss law, Coulomb's law separately. Magnetic field, Ampere's law, Lorentz law separately. You can't do that here. It becomes too vast. So when you're learning Gauss law, you have to learn Ampere's law. When you're learning electric field, you have to learn its counterpart magnetic field. When you're doing some analysis in electric fields, you have to do an equal analysis in magnetic fields. When you're learning electric boundary conditions, you have to learn magnetic boundary conditions. When you're learning capacity, you have to learn inductors. That's how the subject spans. That's how the subject is. So I hope you're getting this, students, all of you. Now, comes the third chapter. The third chapter is about transmission lines, or it's about voltage and current. Here also it's about studying of gamma and characteristic impedance. It's also about gamma and characteristic impedance Z0, just like in second chapter. Second chapter is also about propagation and intrinsic impedance, here the same. The only difference is we study majorly the line and the load interaction. This is most important. Even in second chapter, it's about reflections in the ending. There also we learn about reflections. Here also it is about reflections, no doubt. But it is called as line and load interaction. So that I try to understand line, load, reflection coefficient, gamma, transmission coefficient tau, SWR effects, standing waves. I mean the focus is majorly on this. So no doubt it's about transmission lines, propagation and impedance of the line. But majorly the discussion shifts to line and load interaction, reflection coefficient. And of course study of Smith chart. Very important concept called as Smith chart. Then of course no doubt impedance matching techniques. Impedance matching techniques. That's it. See, third chapter is so simple. It's all about propagation, understanding impedance on the line Z of X, calculations of impedance on the line, understanding of characteristic impedance and Z0, understanding of gamma and tau, understanding of Smith chart, and of course impedance matching techniques. Simple. And the good news is this is one chapter where I don't need vector calculus. This is one chapter where I don't need a coordinate system, because voltage and current are scalar quantities. So they are not vector quantities. That is one good news. So being scalar quantities, it is quite easy for us to handle without any mathematics seriously, without a dot product, a cross product, E bar, H bar. We don't really need to have seriously integrations, differentiations. We don't seriously need to have complications like second chapter and first chapter. Flow is quite simple. Only thing is, GATE will test you with problems actually. The real test comes with the problems. When you have to handle problems, then is when actually the test starts. Fine, that anyhow, when we come into the subject, I'll discuss. The fourth chapter is waveguides. And only two types of waveguides you have to learn. The rectangular waveguides and the cylindrical waveguides. Actually, you have to learn parallel plane waveguides also, but only thing is they only found the backdrop. GATE has asked a question 2 years back on parallel plane waveguides, and again they considered that they gave marks to everybody, maybe accepting that it is not in syllabus. Syllabus is different, your knowledge is different. You will learn a lot of things in the syllabus. You may sometimes skip certain things in the syllabus, but knowledge wise you have to learn a lot of things. So parallel plane waveguides I will be teaching. You have to learn. Through that I introduce rectangular waveguides or cylindrical waveguides. This is chapter 4. And in waveguides it is all about dispersion, understanding of dispersion, understanding of confinement, boundary conditions. So it's more or less simple, and it is majorly problem based. Heavily conceptual topic, but it is still problems based. So waveguides will not test your patience. Like transmission lines, it's also easy. Only thing is you may not need heavy coordinate systems also, because it's only Cartesian coordinate systems. But cylindrical waveguides may test you because they need a basic idea of Bessel harmonics. So slightly when you're learning Bessel harmonics and cylindrical waveguides, then there can be some discomfort levels. Then there may be some toughness, but otherwise, okay, it's quite simple to handle. Then comes the last chapter, that is antennas. Actually, this is going to be a challenge for students, how to prepare antennas. Because antenna starts from what is dipole, what is radiation, and it moves on to Hertzian dipole, half wave dipole, quarter wave monopole, and then from there you have to introduce all the terms and definitions in antennas. What is gain, what is gain, and what is bandwidth, and a lot of things about antennas, like antennas itself is a basic combination of terminologies. So all the terminologies you should be comfortable with. Then comes radiation resistance, is a very important word in the terminologies. RR, radiation distance calculations. So a lot of things will be coming into it. Then comes study of arrays. Very typical important topic even for your post graduation. Even it's important even when you go for some research or anything. Anywhere arrays is quite important. Practically for projects, for PhD work, everywhere arrays is very, very important. So in fact, antennas itself is oriented towards your PhD research and project and those things. So arrays is a very critical topic. When you're learning arrays, you have to learn about end fire array. You have to learn about broadside array. So typically this is what you have to learn. Then we can conclude the subject with Friss free space propagation equation. This is the last topic. Then you can have an overview of all the antennas, overview of all practical antennas. Not part of your GATE syllabus, but you can just have a learning about it. Though it is not in your GATE syllabus, nothing wrong if you learn about practical antennas. Nothing wrong if you handle practical antennas. So this is your entire syllabus requirements. Some people ask me, sir, is there any book to suggest? Some people ask me, sir, can you tell me some books to learn and prepare and become experts? See, books, I can suggest excellent books, give you different names. But GATE is not about books. Because we trainers don't see that you have to learn it from books again. We GATE trainers see that there is a complete information, and that information is sufficient in all aspects. So what I believe is, there is a 3-step approach for GATE exam or for competitive exams. The first is you have to have a conceptual clarity, which is what I'll call it as learning the theory, which is what I'll call it typically as formulae. Some basic formula, some basic subject. Once you are clear with this, you should not need books, because books give you a wide range of case studies in these formulas. The theory is very exhaustive. So if you want books for concepts or theory or for problems, it becomes very complicated. Your life becomes miserable because books present everything, whatever they want. They teach you all possible cases. Textbooks are very interesting. After they give you x plus y whole square formula, they again give a plus b whole square formula also. Which means you are learning things unwantedly two times. So textbooks can't be used as reference and starting for gate coaching and all. Because gate coaching needs something beyond it. It needs a focus level much, much beyond it. So that's why you can't start with textbooks. That's why I'm not suggesting it. We give you books, we give you concepts, we give you training. It should be sufficient. Then comes problems. The second stage is handling problems, questions, which are actually the feel of the previous year questions, PYQs. The previous year questions are very important. That means you should have a very clear idea of what sort of questioning style is being expected. What sort of questions are actually coming, that's a very important clarity you should have. Then comes self-practice. See, if I don't pick up good questions, if I don't do good quality questions, you can do that with self-practice. But that is again cheating from our side. So that's why we see that we do very good quality questions, leave you with very little self-practice. We possibly do every previous year question, leaving you with very little self-practice. So if you want textbooks or if you want self-practice, then textbooks may be useful. Then I don't mind, you can refer. So self-practice wise, maybe you can refer textbooks, or if some teacher has not taught a concept properly, then you can use textbooks. But otherwise in our teaching, when we teach at this level, we see that our problems are complete, our concepts are complete, so that self-practice is only a formality. I'm sure it should not be a very tough thing for you. I hope you got the syllabus. I hope you got the order of strategy. We'll start the first module now. We'll start the first module by understanding what is voltage, what is electric field, what is current, and some basics about static electromagnetics. See you in the first module. So welcome back, students. Welcome back to the classes. We have been trying to understand the syllabus. We have made a beginning in understanding the content. Let's start module 1, static electromagnetic fields. Let's understand this static electric fields and where does it start from, what is it all about. For that, you should all of you know what is voltage, right? So what is voltage, students? Voltage is something that you find when you have an accumulation of charge. Voltage is something that you find whenever there is a huge bunch of charges. Then we say voltage is developed, like in a battery. In a battery, you have some voltages. In the plug, you have an voltage. Because there is a charge accumulation, because of chemical reaction or because of generation. So this voltage, this accumulation of charge is something that you find in materials or devices or conductors. So voltage is accumulation of charge that you find in materials or conductors or devices. So what happens around this material or conductor or device? Around this material or conductor or device, you will find an invisible form of energy around it. So around that material or the device, you can find an invisible energy, some sort of a force of this voltage. So this voltage is having some energy spread all around it. That is what is called as electric field. So voltage is the cause in a device. Electric field is the effect that you find around it. Similarly, you all know what is current, right? Current has got magnetic field around it. So what are the examples of understanding this case study? Take for example a cell phone tower. If cell phone tower is given with some voltage or some signal or some charge, you will find all around the cell phone tower some signal. That signal is electric field. You take for example a satellite. All around this satellite, I find some signal, some electric field. I find some energy spread out, which receives to the earth, which comes to the earth station. That is what is electric field is. Similarly, take for example a Wi-Fi device. A Wi-Fi device being the cause or the voltage containing device, It will have some energy all around it. This energy is what is electric field is. So could be a Wi-Fi device, could be a satellite, could be any example, could be anything, but the point to understand is this. Voltage causes electric field around it. Yeah, it could be a typical capacitor, it could be a simple electric field between the capacitor plate, it could be anything, but typically that's what causes electric field. So what is current? Current is nothing but something that you get because of flow of charges. So whenever charges are flowing, we say that there is a current. This flow of charges or this current always has got something in materials and conductors only. Right. So in a conductor or in a solid device like a satellite or cell phone tower, you can expect some current to flow in it. This current will now have a surrounded energy around it. This energy is called as magnetic field. Some people say, sir, this should be bar magnet, then there will be magnetic field. Bar magnet is a very typical example. Bar magnet is a very rare example. I am not talking about bar magnet. Bar magnet, magnetic field is not what we discuss. We talk about current and current based magnetic field. So the summary of the discussion is current causes magnetic field, voltage causes electric field. This is something that you find in materials. This is something that you find in devices, circuits. This is something that you find in free space. So electric field and magnetic field are the energies spread in the 3D space. They are something that are spread in the 3D space around a circuit or around a device. So let's understand the cause, effect and strength logic now. I hope you're getting the point, students, all of you. We prepared this small animation like thing so that it is easy for you to take over the basics. Rather than me monotonously writing, we thought this animation should be really useful. So how do you understand the cause? The cause is a charge, the cause is an voltage, cause is a charge, then the effect is electric flux. So then we say that the effect around it is a force. But instead of saying the word force, we say there is an electric flux. So if the cause is a charge, students, the effect is electric field around it, electric flux around it, then the strength is called as electric flux density. How strong that electric field is or how strong that electric flux is, that is what is called as flux density. So the common sense is, if the cause is if the cause is charge, effect is called as electric flux, then the strength is called as electric flux density. But look at the units. Charge units are coulombs. So effect also has got the units of coulombs. Then strength has got the units of coulombs per meter square. This is Gauss law. So when I teach you Gauss law, I will call this as Gauss law, no doubt. But right now, if the cause is coulombs, the effect is coulombs, the strength is coulomb per meter square. This is Gauss law. Yeah, no doubt I'll use this Gauss law more explicitly and give some name. But otherwise, look at the cause, strength and effect logic once again. If the cause is not called as charge, charge has got another name, that is voltage. So instead of calling it as charge, if I call it as voltage, then the strength will be called as energy around the voltage, or you can call it as electric field, or you can call it as electric force. So charge is a cause, then effect is called as flux. If voltage is the cause, effect is called as force. Then the strength is called as intensity, electric field intensity. So that units of voltage is volts. So units of effect is volts per meter. This is Coulomb's law. So since voltage is the cause and it has got the units of volts, the effect has got the units of volts per meter. This is Coulomb's law. I hope you're following this, students. So the common sense is this, that you can call the cause as charge or voltage, you can call the effect as flux or force, you can call the strength as intensity or density. Both are acceptably right. Similarly, if the cause is current, then the effect is magnetic force or magnetic energy, then the strength is called as magnetic field intensity. So see that if the cause is current, the effect is magnetic force, strength is magnetic field intensity, and units are typically not volts per meter. Sorry for the editing. It's ampere per meter. It is not volts per meter, it is ampere per meter. This is Ampere's law. So please note that it is not volts per meter, it is amperes per meter here. Then you call it as Ampere's law. Similarly, if the cause is not current and if you call it as any other name like a pole or monopole, and if your strength is called as magnetic flux, instead of calling it as a pole, if you call it as magnetic flux as the effect, then the strength will be called as magnetic flux density. So no doubt the cause is current, but if you give any other name for the effect, if you give any other name for the effect like magnetic flux, then the strength is flux density. So that magnetic flux has the units of Weber, then flux density has the units of Weber per meter square. This is how you understand the complete effects, cause and effects. This is Lorentz law. So ultimately, if you watch carefully, students, I've got 4 laws I've discussed almost. What are the 4 laws? Ampere's law, watch out carefully. Coulomb's law, watch out carefully. Gauss law, and last was Lorentz law, which means I'm talking about 4 major laws which actually will converge into Maxwell's equations. They will be later on called as Maxwell's equations. That is why I'm just recollecting this, students. So that's the 4th law called as Lorentz law. So if you watch out carefully now, what are the 2 measures of strength? You can call it as flux density or you can call it as field intensity. So every electric field or magnetic field, every field, electric or magnetic, has got 2 measures of strength. What are they? Flux density and field intensity. Flux density B or D, field intensity H or E. So units of density per meter square, units of intensity per meter. So intensity is volt per meter or ampere per meter. Density is Weber per meter square or Coulomb per meter square. Hope you're getting this, students. So what are the 4 basic laws of fields? The electric flux density governing Gauss law. Gauss law is governing electric flux density. Electric field intensity is governed by Coulomb's law. Magnetic flux density is governed by Lorentz law. Magnetic field intensity is governed by Ampere's law. These 4 laws will later on become Maxwell's equations. So if you look at intensity versus density, once again D or E both are measuring electric field. So D should be equal to epsilon E. D should be equal to epsilon E, where epsilon is called as permittivity. So in any material, how much is the density or intensity? Depends on the material permittivity. Whether you call electric field as D or E, you may call electric field as density or intensity. The relationship depends on the material permittivity. That is what is epsilon. Similarly, in magnetic field, you may call it as B or H. B equal to mu H. It is not epsilon, it is mu, students. Please excuse me, mu. It's called as permeability. In the cut copy paste, sometimes we forget certain words. So B is equals mu H, where mu is called as permeability. D equal to epsilon E, where epsilon is called as permittivity. So that is a common sense, students. Whether it is electric field or magnetic field, you have 2 measures of the strength. You may call it as density or intensity. Intensity is per unit length, density is per unit area. Intensity is per unit length, density is per unit area. This is a very vital slide. So B or D of electric or magnetic, H or E of electric or magnetic. The relationship is per unit area and per unit length. Similarly, move on to the next point. So what are the 4 basic rules of electric and magnetic fields? Lorentz law, Coulomb's law, Gauss law, Ampere's law. Yeah. Look at how is circuit theory and field theory related. Because see, I'm talking of voltage, current, capacitance, inductance. These are certain things you come across even in circuit theory also. So when you talk about circuit theory and these basics, there should be some relationship. So look at what is circuit theory. In circuit theory, we have Q equal to CV. Coulomb is farad into volts. We have here density is equal to epsilon into E. Coulomb per meter square is equal to farad per meter into volt per meter. Similarly, here we have got flux is equal to Li. Magnetic flux is inductance into current. Then here we have got B equal to mu H. Please, it's not epsilon, it is mu. Same mistake that's here. It's B equal to mu H, where mu is Henry per meter. So magnetic flux is Li, B is equal to mu H. This basic is important, students. Now, the nature of field is that it is majorly 3D. That means it is not something that you find in a circuit like network theory. In network theory, it is simple. You find charge in a device, voltage in a resistor, or current in a circuit. It's about a 2D system. It's all about a simple 2D system. Whereas here it is very 3D. So when it comes to field theory, it is majorly a 3D aspect. So therefore, field is something that's spread in 3D. So you need to have a very good idea of mathematics of coordinate systems and vector calculus. So since it's spread out in 3D space, you have to have an excellent idea of coordinate systems and vector calculus. That is what we'll be learning in this module now. So no doubt it is about intensity, density, Gauss law, Ampere's law, capacitance, voltage, inductance. But it is not just handling about these things blindly. They being vector quantities spreading in 3D space, you have to have a very good idea of coordinate systems. So the subject starts with understanding of coordinate systems. So let's start coordinate systems. Let's go ahead with the next module to understand what is coordinate systems and what are vector calculus. I hope you're enjoying this subject, students. That's very important to enjoy. You should have that zeal and enthusiasm to understand that I'm talking about, I'm talking about 3D space. I'm talking about vector calculus. I'm talking about coordinate systems. And I'm also linking to how it is in circuit theory. The point I'm trying to actually convey is this. The major point I'm trying to convey is, in network theory, it's all about scalar, voltage and current. That's what happens in networks. Why are they scalars? Because there is nothing like direction to handle. Because they're all 2D phenomenon. So they're all scalars because they're all 2D in a circuit. Most circuits are 2-dimensional. Then what makes field theory complicated? Field theory is complicated only because instead of this voltage you have volts per meter. Instead of current you have amperes per meter. Instead of capacitance, C, we have epsilon farads per meter. See, everything is getting per meter. We have mu, which is Henry per meter. Whereas in network theory, we have inductance, which is just Henry. So that's where the common sense is, students. Henry becomes Henry per meter, capacitance becomes capacitance per unit length. So that's where I was telling you that Q coulombs is C farads into V volts. Then volts per meter, farad per meter is coulomb per meter square. Then this becomes D is equal to epsilon into E. So if I simply call it as Q equal to CV, this is networks. But if I say D equal to epsilon E, this is field theory. Similarly, if I say B equal to mu H, This is field theory. Instead of saying magnetic flux is L into I. So magnetic flux is inductance into current, no doubt. But flux density is permeability into intensity. These are some of the basics that govern field theory. So these are some of the cause, strength and effect measures. These are some of the basics I want you to understand, students. So these are the basics of introduction. So let's go on to coordinate systems now. Let's understand coordinate systems and let's try to handle coordinate systems. So hello, welcome back. Welcome back to this coordinate systems session. So I started with the syllabus, content, then I went on to tell you the basics of field theory, what are the terms and terminologies we'll use, what are the laws we'll use, and why the 3D spreading field needs a coordinate system. So let's learn what is coordinate system. So coordinate systems, what do you use for? What is coordinate system meant for? Coordinate system is actually a way of locating, it's a way of identifying points in a 3D space. Instead of saying that point, this point, there, here, below, top, bottom, we say there's a point at 4, 3, 6. There's a point at 8, 9, 4. There's a point at 4 meter, 30 degrees, 75 degrees. So it's a way of identifying points or geometries. We don't say there is a circle. We'll say x square plus y square equal to 9. We don't say sphere. We say x square plus y square plus z square equal to 15. So whenever we are specifying something mathematically, imagination is avoided. So coordinate system is to avoid imagination and give it a perfect picture. That picture is called as mathematics. So we convert imagination into mathematics. Instead of imagining, we convert into mathematics. So that's what this coordinate system is. So it's a way of identifying or locating points or geometries in a 3D space from a well-defined reference. The question comes, what is that reference? Sir, what is that reference, sir? That reference is nothing but the geometry that you are working on. Whose field are you finding out? That reference is that geometry. Are you finding out the field of an antenna? Are you finding out the field of a waveguide? Are you finding out the field of a capacitor? Are you finding out the field of a line charge? So reference is nothing but the geometry that you are handling. It is a cause or the device or the entity around which the field is being studied. You are studying around what? That is what is your reference. So what are the types of references you can have? What are the typical types of references? A reference can be a simple plane, it can be a line, or it can be a point. In 3D space, there are 3 different possible references. What are the 3 references? It can be plane or sheet. It can be plane or sheet, then it is called as Cartesian coordinate system. So if your reference is a waveguide, capacitor plate, if your reference is any planar geometry, we call it as Cartesian coordinate system. If your reference is an axis or line, if your reference is a typical axis line, we call it as cylindrical coordinate system. If your reference is a simple point, and if your reference is as simple as a point, we call it as spherical coordinate system. So coordinate system depends on what reference are we choosing. What is your geometry that you have to handle? Is the geometry simple point? Is the geometry in the form of a sphere? Is it a satellite seen from the earth? Is it a current wire that I am handling? That decides your reference. So, what are parameters? Parameters are nothing but the ways of addressing this coordinate system. Way of addressing this coordinate system. So, what are parameters, students? Parameters in Cartesian coordinate systems are typically nothing but x, y, z. They are nothing but x, y, z. So, what are your references? The references are nothing but x, y, z, zx planes. So parameters are x, y, z because your planes are called as x, y, z and zx plane. Similarly, what is your reference called as in cylindrical? It's called as z axis. Similarly, what is your reference called as in spherical? It's called as origin. So your reference and the parameters of addressing will depend on this. In Cartesian, it is x, y, z, zx plane. In cylindrical it is z-axis, in point it is called as origin. So what will be your parameters then? In Cartesian the parameters are called as x, y, z. In Cartesian the parameters are all three distances. In cylindrical they are called as rho phi z. One distance, one angle, one distance. Means two distances and one angle. What about in spherical? One distance and two angles. That means coordinate system is getting more and more complicated. Expression is getting more and more complicated. What I am trying to tell you is, if it is Cartesian coordinate system, the reference is quite simple. The parameters are simple, all the three are distances, addressing is simple. If your reference is getting as a line, the expression is getting more complicated. It needs directions, it needs distances. And if your reference is getting as simple as a point, it is more complicated because there are multiple directions involved. So addressing from a point involves multiple directions, horizontal, vertical. Addressing from a line has only one single direction. Addressing from a sheet is of course very simple. I have introduced you in this session to why we use coordinate systems and what sort of coordinate systems we have got. That's what I have introduced you. So in this session I will tell you how actually coordinate systems are to be understood. The summary of what I am trying to teach you students in the last few minutes, what I was trying to teach you is, in Cartesian coordinate systems, there is an x, y, and there is also a z-axis which is out of the board like this. So don't draw this z-axis on the board and make it too 3D and confusing, so that you are overlapping this z with x and y. Don't do that. Keep your z-axis out of the board so that the board is right now xy. When it comes to cylindrical coordinate systems, you only have a z-axis and don't show the x and y. And its center will be somewhere here, which is z equal to 0 or origin. So with respect to this center, you have to refer and address everybody. With respect to this xy, you have to address everything. In spherical coordinate systems, even this z-axis won't be there. Only origin will be there. But in textbooks, they won't show like that. Here also they will show xy. Here also they will show xy. And create lot of confusion. So in textbooks, what happens is they will show you x, y, z here. And that is z on the board itself, again mixing with the two dimensions. Here also they will show x, y and z. Here also they will show x, y and z. Don't do like that. That will create lot of confusion. What I am trying to tell you is, if it is Cartesian coordinate systems, you have x, y, z out of the board. You got z-axis and you got origin. And here the addressing parameters are x, y, z. Here the addressing is with r theta phi, and here the addressing is with rho phi z. I hope you are getting it. So let's start with Cartesian coordinate systems. Let's start the discussion with what is Cartesian coordinate systems. Cartesian coordinate systems is something where the distances x, y, z are used to address any point. So if this is x and if this is y with z out of the board, so what is this called as? This is called as yz plane. So what is this is yz plane? What is this? This is zx plane. So then what is x called as? X is shortest distance from the yz plane from here perpendicular distance to the point. Sir, what if my point is here? Is this the distance? No. If your point is here, drop a perpendicular. This is shortest distance. Sir, what if your point is here? Drop a perpendicular. This is x. This is x. Right side is x positive, left side is x negative. So what is x therefore? Shortest or perpendicular distance. Shortest or perpendicular distance of the point from YZ plane. And what is the range of x supposed to be? X goes from minus infinity to plus infinity. So every point in the world is at any positive distance or is it any negative distance on the left side or on the right side. So that addressing is complete. So is y now. So what is y supposed to be? Shortest distance from zx plane. What is z supposed to be? Shortest distance from xy plane. So shortest distance from xy plane is z, y is from zx plane, then obviously x is from yz plane. I hope it's getting clear, students. That's how you understand the parameter first and its range. The next is a few set of definitions. A clarity on a few set of definitions. So that is a clarity on, see for example, what is a geometry or what is a shape which is defined as x is equal to 4 for all y and z. What is the geometry of all the points with x equal to 4 for all y and z? You should say it is an infinite sheet. It is an infinite sheet. How is this infinite sheet? It's parallel to YZ plane. It is parallel to x is equal to 0 plane. But interestingly, I can also say it is perpendicular to x-axis. So when I say x is equal to 4, it is an infinite shape which is parallel to the YZ plane. It's parallel to the x equal to 0 plane, but it is also perpendicular to x-axis. That is, if you have this as x-axis, if this is y-axis, z-axis is out of the board, this is also x equal to 0. So all these points are at x is equal to 0 because you are not going away from them, you are not going towards x-axis. This is what I call it as x is equal to 4. So all these points are x equal to 4, which may be out of the board or on the board. They may be on the board or they may be out of the board. This is x equal to 4. So clearly perpendicular to x-axis, parallel to the YZ plane, parallel to x equal to 0. I hope you're getting it. Now, when I said x is equal to 4 for all y and z, this is infinite sheet. What if I say x equal to 4, y equal to 3 for all z? One dimension was constant, two were variable. One dimension was constant, two were variable. Then it was actually a sheet. Now, two dimensions are constant. And one is a variable. So when two dimensions are constant and one is a variable, how does it look like? it looks like a line now. That is, now on this x is equal to 4, I am talking of 1 point, y equal to 3. This is x is equal to 4, y equal to 3. For all z means out of the board. So x is equal to 4, y equal to 3 for all z. That is nothing but a line parallel to z-axis. So this is the way of identifying things, students. So next time when you see any definition, you should know what is it being discussed. What are the variables, what are the constant? Then mark accordingly. Because every time I won't say there is a line. I will say there is a geometry y equal to 4, z equal to 7 for all x. It means I am talking of a line parallel to x-axis. So whenever I talk of a geometry, whenever I talk of a shape, you should have a clarity. And the clarity is how many dimensions are constant and how many dimensions are variable. What is its shape? So once again look at it. X is equal to 4, yz variable. This is nothing but an sheet. Similarly, x is equal to 4, y equal to 3, z is variable. This is nothing but a line. And if I have got x is equal to 4, y equal to 3, z equal to 6, this is a point where all the 3D are fixed. Here 2D are fixed. Here 1D is fixed. 2 variables, 1 variable, 0 variables. This is Cartesian coordinate systems. Now, in Cartesian coordinate systems, how do we extend things? We extend things by again understanding something called as unit vectors. Because every vector is complete in the form of a magnitude and a direction. So when a vector is complete in the form of magnitude and direction, magnitude we express it through parameters. 4x square, 2x. Then direction, how do you express it with? Through unit vectors. So every vector in the world is a combination of magnitude, which is a combination of parameters, which is any f of x, y, z. In what direction? According to the unit vector, it can be ax. What if it is in y direction? Then g of x, y, z, ay. What if it is in z direction? Then it is h of x, y, z, az. So every vector in the world is expressed through parameters and unit vectors. Parameters and unit vectors. Parameters will give you magnitude. Unit vectors will give you direction. So it's mandatory to know the directions. It's mandatory to know your unit vectors. So what are the unit vectors? Ax, ay, az. Or you can call it as ux, uy, uz. Sometimes even call it as x cap, y cap, z cap. Sometimes even maths teacher call it as I cap, j cap, k cap. So these are the different notations for unit vectors. I use this notation. So tell me, what is Ax? Ax is no doubt a unit vector. Unit vector in the direction of x increasing by maximum. How should you go so that the direction or the vector is increasing by maximum? That direction is what is Ax. So Ax is a unit vector in the direction of maximum increase of x. So suppose if you look at here, I want to get the unit vector Ax direction here. So when I want to get the unit vector Ax direction here, if I go like this, x is not increasing by maximum. It is increasing, no doubt, but it is not by maximum. If I go by the same length this side, it is increasing but not by maximum. But if I go like this is maximum increase. So Ax direction is always the direction of increase of x by maximum, which is direction perpendicular to yz plane. It is a direction perpendicular to yz plane. It is a direction perpendicular to x is equal to constant surface. Because don't forget that yz plane is x is equal to 0 also. So if you go perpendicular to yz plane, that's what is Ax direction. But that is also the direction perpendicular to not only x is equal to 0, but also for x equal to 4, but also for x equal to 10. So Ax direction is always the direction in which if you go, x increases by maximum. So it is perpendicular to yz plane and also to x constant. Don't go along x being constant, go along x increasing. Go along x increasing rather than x being constant. So obviously they are perpendicular to each other. I hope this point is very, very clear to you. Right? So this being coordinate system basics, I summarize the discussion once. That I taught you that Cartesian coordinate systems, there can be scalar functions. There can be scalar functions, means quantities which depend on space, as any f of x comma y comma z. This is called as a scalar function which is depending on x, y, z space. Typically there can also be again vector functions which are quantities which depend on space along with the predefined direction Ax, or they can be a function of space in a specific direction Ay, or they can be a function of space in specific direction Az. I taught you what is the definition of Ax, Ay, Az. I taught you what is the definition of x, y, z. That's coordinate systems. That's Cartesian coordinate systems. Cylindrical coordinate systems is slightly tougher than this. Spherical coordinate systems obviously becomes a bit more tougher. But otherwise, coordinate systems, Cartesian coordinate systems is one of the easiest. But only thing is, when I taught you, I was going through the hardcore definitions. And understanding the definitions is very important. Why? Because everything depends on those definitions. Everything depends on those basics and those definitions. That's why it's damn important, right? So see you with cylindrical coordinate systems. Let's start with cylindrical coordinate systems now. So hi, welcome back. On coordinate systems, we have started with why we use coordinate systems. Then later on we understood how to use coordinate systems. Then we understood what is Cartesian coordinate system. Now we'll try to understand what is cylindrical coordinate system. So the agenda is now to understand what is cylindrical coordinate systems. In cylindrical coordinate systems, as I told you, The reference is only a z-axis and there is its origin. You have to find the points all around it from this z-axis, for which the parameters that you got are rho, phi and z. So you got only 3 parameters to handle and the 3 parameters are rho, phi, z. What is rho supposed to be? Rho is supposed to be perpendicular distance or shortest distance. You can either call it as perpendicular distance or shortest distance. From where? From the z-axis. So rho is supposed to be shortest distance or perpendicular distance from the z-axis. So you may have a point at this point, then this is its rho. The same point could be here, this is its rho. If the same point is here, its rho. The point could be somewhere here, this is its rho. So rho is nothing but the shortest distance. By dropping the perpendicular you get it. By dropping the perpendicular you get shortest distance rho. So what is the range of rho supposed to be? Anything from 0 to infinity, left side also 0 to infinity, out of the board also 0 to infinity, behind the board also 0 to infinity. So it goes anything from 0 to infinity. So rho is nothing but shortest distance and it can go anything from 0 to infinity. So suppose if I have z-axis, origin, and if I have rho equal to 5, what is the possible location of these points? Possibly, where are these points located? They could be possibly located at a distance of 5 on both the sides, out of the board, and all around it. So they are located at 5-meter distance all around it. So rho equal to 5 means your possible location is on a cylinder which is concentric with the z-axis. That means z-axis is the cylindrical axis. So the cylinder's axis is supposed to be z-axis and you get a cylinder forming with rho equal to 5. Your points can be anywhere on this. I hope you are following this, students. Then what is phi defined to be? What is phi? Phi is supposed to be direction. Phi is supposed to be direction or angle of the point around z-axis. So in what direction it is around z-axis? Is it in phi equal to 0 side? Is it in phi equal to 180 side? Is it in phi equal to 90? Phi 270 behind it? So phi is all around this z-axis. If this is z-axis, it's all around it. So phi is therefore, this is phi. This is what phi is. So on the board if you see now, let's say this is phi equal to 0 degrees. Then left side phi equal to 180 degrees. And now phi is around the z-axis like this. This is what phi is. Phi is always around the z-axis. So if somebody asks you, show me phi in this diagram, I cannot show you. Because in this diagram phi is out of the board or behind the board. So what should we do for looking at phi then? If you want to look at phi, you have to see your z-axis coming out of the board and you can see now phi around z-axis. This is phi. starting with phi 0 degrees somewhere here, going to phi 90, phi 180, phi 270. So phi is around z-axis. Where is rho? Rho is away from z-axis. This is rho. This is rho. So rho from the z-axis, phi around the z-axis. Rho from the z-axis, phi around the z-axis. So if somebody asks you, what is the geometry? What is the geometry of all the points with rho equal to constant for all phi and z? What is the geometry of all the points with the rho equal to constant for all phi and z? The answer is, it is nothing but a cylinder. If somebody asks you what is the geometry of all the points with rho equal to constant, phi equal to constant and all z, on this cylinder in a specific direction. I hope you are getting this. This actually forms a line for all z. Because if you watch carefully, rho equal to constant is this value, let's say some value, rho is some phi, and again I am saying phi is constant. Let's say phi is some 60 degrees. So this is what is for all z. So it is a line parallel to the z-axis like this. So this is z-axis. This is one more line parallel to it. So typically, rho equal to constant, phi equal to constant forms a line. Now comes what is z? Z is supposed to be height of the point along this line. Height of the point along z-axis. At what height the point is? That's what z is. Is it 2 above or is it 2 below? So z defines at what height it is. So rho defines at what distance it is. Phi defines in what direction it is. Z defines at what height it is. Is it at z equal to 0 height? Is it in z negative or is it z positive? Is it above or is it below or is it exactly at the center? This is cylindrical coordinate systems. So range of phi goes from 0 to 2 pi, completely around. Range of z goes from minus infinity to infinity. So that you are in a position to look at every point in the world, where you can now look at every point in the world, because if this is z-axis, you could be at any rho, you could be at any z, you're at any distance from it, you're at any height from it, and you could be in anywhere out of the board or behind the board, out of the board or behind the board. So that's exactly what rho phi z means. So distance from this z-axis, direction around the z-axis, and height, they make coordinate system interesting. The point in textbooks is, what happens in textbooks is, actually the problem with textbooks is, instead of keeping it simple like this, they complicate it. That is, instead of showing a view, instead of showing a z-axis, y-axis, there is no need of showing this xy plane. You can simply call it as z equal to 0. But instead of calling this as z equal to 0 height, they show you typically as xy plane. This adds confusion. Why Cartesian terms are coming in cylindrical? Because z is common. So, no doubt when you have xyz notation and rho phi z notation, z being common, it is okay to interchange x and y with rho and phi. It's okay, you can. So that's why most textbooks, what they do is, instead of calling it as z equal to 0, they also show xy plane. Similarly, if you look at the other view, where z-axis is out of the board, the z-axis is not on the board but it is out of the board, they show x and y. So that it's very clear that from x-axis, you start counting for phi equal to 0. So instead of showing phi equal to 0, they show x-axis, so that it is starting for phi. Similarly, instead of saying z equal to 0, they show xy plane, starting for z, starting for x. And how does phi go then? Phi goes anti-clockwise, because right hand folds like that. So phi therefore goes around. This is how phi is. Phi is around it. So phi 90 degrees is here, phi 180 degrees is here, phi 270 degrees is here. So no doubt putting xy imposing on cylindrical also helps. Imposing xy on cylindrical, no doubt it helps. But still there is a necessity to understand cylindrical independently. Even if there is no xy also, you should be in a position to understand that phi is around it and z is along it, rho is away from it. So once again I repeat this word, students. Rho is from z-axis, phi is around z-axis, and z is along z-axis. So these are three words that I hope you can remember always. Keep these words clear in your brain. From, around, along. From the z-axis, around the z-axis, along the z-axis. I repeat this once again. If this is z-axis, from the z-axis, along the z-axis, around the z-axis. From, along, around. This makes cylindrical coordinate systems. Now comes spherical. In spherical, it's much more easy to start with, because in spherical there is only one origin. And you have to address all these points around it with respect to this origin. The point could be on the board, it could be out of the board, could be behind the board. The point can be here. All you need to do is to address this from the origin. So let's see how the student handles it. Let's see how you have to handle it. So given that origin is the reference, given that I have only origin as the reference, I'll first of all take a vertical line and call this as theta equal to 0 degrees line. Sir, why are you choosing the theta equal to 0 degrees line? So that I can start showing some angles. Because angle needs to start from somewhere. So I'm showing that starting angle as theta equal to 0 degrees. Or also I can call this as z-axis. Sir, but why are you superimposing with cylindrical? Because when I shift from rho phi z notation to r theta phi notation, I have phi common. So since my phi is common in both the coordinate systems, I can comfortably shift from r theta phi notation to rho phi z or rho phi z to r theta phi, keeping that phi common. So I'll show this as z-axis. So my z-axis is ready. My z-axis is ready, or my theta equal to 0 is ready. That means I am able to superimpose cylindrical and spherical also. Theta equal to 0 degrees. This is origin. So what is the parameter r? What is theta? What is phi? What is r supposed to be? R is supposed to be radial distance or shortest distance from the origin, from the reference. So r is supposed to be the shortest distance or radial distance from the origin, means at what distance you are from here? Are you at this distance? Are you at a bigger distance? Are you at a much bigger distance? At what distance you are, that's what is r is. So r typically tells you that you are at any distance, which means you are on anywhere on the sphere. So r tells you that your possible address is anywhere here. This is where r is. Then what is theta supposed to be? Theta is supposed to be the vertical elevation on this sphere. At what elevation are you in? Are you at this elevation? Are you on this elevation? Are you at this elevation? Or are you below? Are you much below? So theta tells you at what elevation you are in. So how do you identify theta? Theta is this angle with this 0 degrees. So therefore, if you understand that this is z-axis, if you understand that this is theta equal to 0 degrees, if this is z equal to 0, from here this angle is what is theta is. So theta is vertical elevation angle from the origin. Theta is vertical elevation angle. So what is theta supposed to be, students? Angle from here. Sir, should it be only this side? No. Theta can be on this side also. Sir, should it be only on the board? No. It can be out and behind. Out and behind. So from my eyes, watch out from my eyes, this is theta. I can also see this side, this is also theta. Same elevation. See, I am looking at one elevation. Same elevation. So that elevation can be in all the 4 directions. Same elevation, north, east, south, west. So you can have the same theta in 4 different directions. That is what is theta is. So what is theta supposed to be? Theta is supposed to be vertical elevation angle from the origin. It's vertical elevation angle from the origin. So if you watch carefully, this is origin, this is z-axis, this is theta equal to 0 degrees, this is z equal to 0. I have an r constant sphere located to me. This is r equal to constant sphere. At an elevation of theta degrees, there can be few points this side, few points this side. These are the points. This is theta. So what is theta giving me? Set of points on this sphere at a given height. So on a r constant sphere at a constant elevation, these points are there. So with this theta degrees, I am talking of these points. So what if theta is 0 degrees? If theta is 0 degrees, I'll get exactly 1 point and this is the top. What if theta is much bigger? I'll get these points. What if theta is 90 degrees? If theta is 90 degrees, I'll get these points. Points which are exactly at the center. What if theta is greater than 90? I'll get these points. What if theta is 180 degrees? I'll get the exact bottom point. So that's a common sense. That's the common sense, students. So the common sense is ultimately that if you have a sphere of r equal to constant, if you have a sphere of r equal to constant, different thetas will give you different circles at different heights. Different thetas will give you different circles at different heights. This is theta equal to 0 degrees height, 30 degrees height, 60 degrees height, 90 degrees height, 120 degrees height, 150 degrees, and this is 180 degrees. So what is the range of theta? Starting from 0 degrees to 180 degrees. It starts from 0 degrees and completes to 180 degrees. So range of theta is therefore, what is the range of theta? 0 to 180 degrees or 0 to pi. What is the range of r? 0 to infinity. Range of theta is 0 to pi. What is phi then? So now that sphere is located with r, from the origin sphere is located with r, theta is giving you circle on it, phi tells you where the point is. So from origin r distance sphere located. On that sphere circle height is located. Your point height is located. Circle is located. On that circle where exactly the point? That is phi. So phi is on this circle, where is it? On this circle, where is it? On this circle, where is it? So what is phi? Phi is horizontal direction. It is horizontal direction around the origin. So it tells you at what direction your point is, horizontally around. So that's exactly what I'm trying to teach you, students. That if this is your origin, R tells you at what distance you are in, which can be on the board, out of the board, anywhere. So your possible location is this sphere. Your possible location is this sphere. Now on this sphere, what does theta tell you? Your possible location as this circle or this circle or this circle. So starting with theta 0 degrees to 90 degrees to 180 degrees. It tells you what is your circle or where is your circle possibly. Then comes most importantly phi. What is phi? Phi tells you at what direction your point is. So this is theta. This is theta. This is theta. So theta tells you vertically, phi tells you horizontally. That's what is latitudes and longitudes. That's what you call them as coordinate systems on the earth, locating points on the earth. This question was asked in GATE 2024, testing this knowledge. So that's the common sense, students. That's the common sense. R defines radial distance from the origin, theta defines vertical elevation angle, phi defines horizontal direction. Now to continue this discussion, what is damn important is unit vectors, because I finished defining what is rho phi z, what is r theta phi, what is xyz. This definition is over. You should now learn what is a rho, a phi, az. You should now learn what is ar, a theta, a phi. So what is a rho supposed to be? A rho is the direction in which if you go rho should increase by maximum. A rho is the direction of increasing rho. So a rho is the direction in which if you go rho increases. So how does this a rho look like? If this is z axis and if this is its center, you can go radially to the right and increase rho. You can go to the left and increase rho. You can come out of the screen and increase rho. This is a rho. A rho is a multi-directional vector. It is not in single direction. It's a multi-directional vector. This is a rho. This is a rho. So if you look at its top view, look at the top view. This is z axis. So a rho is radially to the right, to the left, to the bottom. This is a rho. So how is a rho? Radially away from the origin. Multidirectional vector. What is a phi? A phi is the direction which if you go, phi increases by maximum. A phi is the direction which if you go, phi increases by maximum. So how does phi increase? Phi increases as you go around. This is how phi increases. So phi increases as you go around, starting with phi equal to 0 degrees to 90 degrees to 180 to 270. This is a phi. This is a phi. Now beautifully remember that it is anti-clockwise, because the right hand folds anti-clockwise when the thumb is out of the board. So thumb out, right hand folds anti-clockwise. So a phi is around z axis, and it comes out of the screen and it goes anti-clockwise. Beautiful to notice. Just notice a beautiful analogy. This line arrow is perpendicular to a phi. Beautiful to notice that arrow is perpendicular to a phi, and az, which is parallel to z axis, is out of the board, parallel to this, that is perpendicular to both. So just like AX is perpendicular to AY, is perpendicular to AZ, is perpendicular to AX. Arrow is perpendicular to A phi, is perpendicular to AZ, is perpendicular to arrow. They're also perpendicular. So the common sense is this, students, that arrow, A phi, AZ are perpendicular to each other. They form an orthogonal pair. The same analogy continues even in spherical coordinate systems. So watch out spherical coordinate systems. If this is origin, what is AR supposed to be? Radially outward vector from the origin. It is the direction of R increasing. So what is AR supposed to be? AR is a direction which if you go, AR is a direction which if you go, R will increase by maximum. This is AR. What is A theta? A theta is something in which if you go, theta should increase. This is A theta. So very clearly, A theta increases from theta 0 degrees to 90 degrees to 180 degrees. This is A theta. So 0 degrees to 90 degrees to 180 degrees. And how is orthogonality here? Perfectly orthogonal. Because AR is clearly perpendicular to A theta. How is A phi then? A phi is out and into the board. So A phi is out of the board here and into the board here. Because A phi is like this. This is how A phi is. So A phi is around, A phi is around, comes out of the board and goes into the board. So A theta vertical, A phi horizontal and AR radial. Radially outward, vertically from top to bottom, horizontally around. Horizontally around, vertically top to bottom. See, vertical is like this, horizontal is like this. They're orthogonal obviously. So AR is perpendicular to, A theta is perpendicular to, A phi is perpendicular to AR. This is pakka. So common sense is basic orthogonality rules they obey. So finally, if somebody asks me what is a summary of what I taught you, I taught you what are the parameters and what are the unit vectors. I taught you what is x, y, z. I taught you what is ax, ay, az. I taught you what is rho, phi, z. I taught you what is a rho, a phi, az. I taught you what is r theta phi. I taught you what is ar, a theta, a phi. This is the summary of learning coordinate systems. Step 1 of coordinate systems. From here you can improvise. You can do a lot of questions. But the basic I expect from students is they should have a command over these things. The basic I expect from students is they should have a minimum command over what these mean. What these parameters mean actually. So once again, let's summarize this discussion. X, Y, Z axis. This is a complex system and the parameters are distances from this system X, Y, Z. Then there is a simple system with a complex addressing mechanism. System is simple, that you only have a Z axis. Then from the Z axis, distance, height, directions, that makes it complicated. from the z-axis distance, height around, that's what is rho phi z, and respectively unit vectors also. Then there is a system called as just origin, from where there is again r, theta and phi. So r from the origin, theta and then phi. So r from the origin, theta and then phi. This is coordinate system, students. This is the basics of coordinate systems. Now we'll do some questions on coordinate systems so that you get some confidence on coordinate systems. Because without problems, without questions, you cannot get confidence. So let's continue questions on coordinate systems. Let's have a look at it.